All right, everyone, here we go. So today we're taking on our Quiz 6 review. So what I've done is I've pulled problems that are from old homework assignments that I know typically are trouble problems for students. So first up, I'm looking at my diagram, and I see that I have a tangent and I have a radius. So I know that they are perpendicular. So I know I have a right triangle right there. Okay, I also know that this part of it is x, so this part right here must also be x because that is also a radius. So right here, let me fill that in as x as well. Okay, and then from here, usually I do a little sketch, quick sketch of the right triangle. So I have x, I have 12, and then this full span is x plus 8. All right, so from here, I know I'm just using the Pythagorean Theorem, so a squared plus b squared equals c squared. So here I have x squared plus 12 squared equals x plus 8 squared. So now as I work through it, I have x squared plus 144 is equal to x plus 8 times x plus 8. And then I'm going to have to FOIL this out. So again, left side, I still have x squared plus 144 is equal to, there's my first, x squared. My outer is plus 8x. My inner is plus 8x. And my last is 64. So here, let me just do one more stage of cleanup, consolidate those like terms. So I have x squared plus 144 equals x squared plus, well, the 8x and the 8x here makes 16x total plus 64. So from here, I can see that I have a quadratic term on my left-hand side, and I have a quadratic term on my right-hand side. So if I subtract x squared away from here, for example, it's going to subtract away from here as well. So I'm just going to go ahead and cancel those out, cross them out. And now I have a linear equation. Now I have 144 is equal to 16x plus 64. So now I just have to subtract away the 64, gives me 80, and 80 is equal to 16x. Divide that 16 away, and we get that x is equal to 5. Okay, next one, similar idea. So we're starting off with a tangent, right? It's touching the circle in one spot. That's my point of tangency. And here's my radius. So I know that if my radius is 3, I know that right here that span has to also be 3 because any radius has to be congruent to any other radius. So again, I'm going to use that strategy of just drawing out the right triangle off to the side. So this leg is 3, this leg is 6, and this hypotenuse is x plus 3. So now if I use Pythagorean Theorem, now I have 3 squared plus 6 squared equals x plus 3 squared. So 9 plus 36 equals x plus 3 times x plus 3. So here I'm going to have to FOIL that out again. So first, outer, inner, last. On this side I have 45. So 45 is equal to, here's my first, the x squared. Here's my outer, 3x. Here's my inner, 3x. And here's my last, the plus 9. And then again, I'm just going to consolidate. I'm going to combine those like terms. So 45 equals x squared plus 6x plus 9. All right, so I can see that it's a quadratic. I usually hope that I can factor, so let's see if we can factor. First thing that we have to do, though, is make sure our equation is set equal to 0. So I have to take away the 45 from each side. So now I have 0 is equal to x squared plus 6x minus 36. So here I'm going to stare at that for just a moment and think in my head, can I think of two numbers that would multiply to a negative 36 that would add to a positive 6? Okay, and I work through all of my options, and I should realize, not going to factor. Does not factor. So then I have to run through my list of other options for how to solve a quadratic. So I could solve by taking the square root, right? That option really doesn't work here because I have a linear term. I have that 6x. Okay, factoring. Well, factoring didn't work for me here. Okay, so another option would be using the quadratic formula. That's what we practiced earlier on in the week. Okay, or we could do this process of completing the square, which I have not reviewed with you just yet. So we're going to have to go back and use quadratic formula. So to remind you of what that is, over here I'm going to write it in green. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So there is our quadratic formula. The a value here is the quadratic coefficient, 1. The b value is the linear coefficient, so 6. And the c, right, that's my constant, the negative 36. So x equals negative 6 plus or minus the square root of 6 squared minus 4 times 1 times negative 36, all over 2 times 1. Okay, and then from here, I'm just going to clean it up. So I'm going to get negative 6 plus or minus the square root. Well, I have 36 here, and then remember here's where I usually see a mistake. So this whole part right here, that is a package. That is a product. So I'm looking at what's negative 4 times 1 times negative 36. And that's going to give me positive 144, all over 2. Okay, one more little cleanup. So negative 6 plus or minus the square root of 180 all over 2. So here I have to think, well, what is the square root of 180? Let me move it over here where I have more room. So if I simplify that, I have negative 6 plus or minus 6 root 5. Okay, so here the square root of 180 is really 36 times 5. So since that 36 is a perfect square, that's why I have 6 on the outside times the square root of 5. So then all divided by 2. And then I'm really looking to see, well, what are these three numbers? All three of them, all divisible by? They're all divisible by 2. So this cleans up even more to be negative 3 plus or minus 3 root 5. Okay, but that's giving me two answers. I have negative 3 plus 3 times the square root of 5, and I have negative 3 minus 3 times the square root of 5. Well, I'm not going to take the one that gives me a negative value because I can't have a negative measurement here. I'm only interested in the positive. So I'm only taking that negative 3 plus 3 root 5. So algebraically, there were two solutions, but when we apply it to a length, a measure in geometry, we're only interested in the positive. All right, next up, what is the radius of circle C? Well, when I look at my picture, I actually don't have any radii marked. The radius would always be connecting the center to any point on the circle. So I can draw one in. So let's draw in a radius like so. So now I have a right triangle. Let me draw it off to the side. Okay, I should remember that when I have a radius, so if I drew in this whole radius pathway, and it's running perpendicular to a chord, that chord gets bisected. So right now, this chord is split into two equal parts that are both 8. So when I'm looking at this triangle right here, this right triangle, I have a longer leg that's 8 and a short leg that's 4, and I'm solving for the hypotenuse. So now I'm just going right back to Pythagorean Theorem. So 4 squared plus 8 squared equals x squared. So 16 plus 64 equals x squared. X squared equals 80. I solve by taking the square root. So 80 is 16 times 5. So I know that I'm going to get plus or minus 4 square root 5. So again, algebraically, I got these two solutions, but when I apply it to a length or measure in geometry, I'm only taking the positive. So I get 4 square root 5. All right, next up, find the degree measure of the arc. So remember our starting formula that we talked about. We talked about how the length of the arc is equal to the ratio of arc to full circle. And we know that the intercepted arc will match the central angle as well. So here I'm looking at first degree measure over 360 of the arc and of the central angle. Same measure here. And then I multiply that by the circumference. So this was the first formula that we used. But here I'm asking for the degree measure of the arc. So I'm asking for the m. So I just want to remind you that we solved our equation for m. We used a little bit of algebra to get there. We cleared the fraction by multiplying by 360, and then we divided by the circumference. So we got this beautiful new formula, which is just isolating the m instead of the l, 360 times the length divided by the circumference. And we know the importance of parentheses to preserve our order of operations. So when I look here, I can say that 360 times the length, right here's the length in units, is 35.69. And then I'm going to divide that by 2 times pi times my radius here of 20. Again, I need parentheses around the top and around the bottom, just like so. So when I plug in and I get a degree measure to the nearest hundredth, I should be getting 102.24 degrees. Okay, one other thing just to point out here is that I could also just plug straight into this formula instead and then use my algebra skills to isolate the m. So in this case, I could plug in the length right here, the 35.69, and the radius here, the 20, and then again, just rework my equation to solve for m. So that's another pathway through the problem. All right, next up, find the indicated angle or arc. So in this one, what I'm seeing is that I have an inscribed quadrilateral. We know that quadrilaterals, all of these angles have to sum to 360, and we know that the angles that are in the opposite positions, they're going to be supplementary. They're going to add up to 180. So I know first off that these have to sum to 180. So let's make an equation. I know that x plus 5/4 of x will equal 180. Okay, and then, well, I want to clear my fraction, so I want to multiply every single term by 4. What I do to one, I do to all of them to keep the balance of my equation. So I really have 4x plus 5x equals 720. So now I have 9x equals 720. Divide by 9, and I get 80 for x. So I have 80 degrees right here. 5/4 of 80 will be 100 over here. Okay, for these angles that are in opposite positions, same thing. They have to be supplementary. They have to add up to 180 degrees. So here I can say that y plus 4/5 of y will equal 180. And again, I have to clear my fraction, so I'm going to multiply every single term by 5 to maintain the balance of my equation. So now I have 5y plus 4y equals 900. 9y equals 900. Okay, divide each side by 9, and y equals 100. So right here, this is 100. And 4/5 of 100 is going to be 80. So 80 degrees right there. So the measure of S, so right here where S is, there is 80 degrees. The measure of N right here is 100 degrees. And the measure of arc NP, so from here to here, right? So that's calling it a minor arc. It has to be less than 180 degrees. So I can see that right here, that inscribed angle, vertex is on the circle, is 80. So as I go out to the intercepted arc, I have to double that 80 and get to 160. Okay, next one here in B, we see that we have this inscribed regular hexagon inside of a circle, and we have a few extra chords drawn in as well. All right, so first thing again, when I have an inscribed regular hexagon, I can visualize, oh, I have 6 congruent chords. So I know that my arcs of congruent chords, they're always going to be congruent too because they cut off the same portion of the whole circle. So to find each of those arcs, I'm just taking 360 and I'm splitting it 6 ways. So 60 degrees here, 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 and here. I know it's not perfectly to scale. We do the best we can. All right, so now as I move my way around my circle, I can look for any inscribed angles. So here vertex is on the circle, so this angle has to be half of 60, so 30 degrees. Okay, over here where S is, well, if I trace it up, here, this would be 240, so half of 240 has to be 120. And over here, this angle has to be half of the 60, so 30 right here. That makes total sense because I can see that right here I have an isosceles triangle. The vertex angle is 120, and those base angles, they're both 30 degrees. Okay, sliding over right here. So this angle, this is its intercepted arc, so half of 60 will be 30 degrees. Okay, if I go over to here, these sum to 120. Half of 120 is 60 right here. Okay, over here, this one, so trace it over. Half of 180 would have to be 90. So it's also then telling us that this has to be a diameter of the circle, right? Because it creates the 2 semicircles that are both 180. Over here, half of 120 gets me 60. Okay, over here, tracing it up, also half of 120 gets me 60. Okay, all of that is making sense because look at all of these interior angles. Look at this full interior angle here, this full one here, this full one here. You can see that they're adding back up to 120, just like we're seeing for that one. All of the interior angles of the regular hexagon, they should all be 120. That's just going back to this formula that we learned earlier this school year. So n minus 2 times 180 divided by n. So if I apply that to a 6-sided figure, I get 720 degrees total split 6 ways, and that's just confirming what I've been saying about that 120 degrees. So right here, I know that it should be 120. Let's just double check it. So if I trace it up, is half of 240 120? Absolutely. So 120 right here. And then same thing here, if I trace that up, here's 240 again, and half of 240 is 120. All right, so filling in my gaps to the right, measure of arc, RA, is 60 degrees. BRI here, that's a semicircle, so 180. Angle NBI right here is 30 degrees. BNI, so BNI right there is 90 degrees. BSN right there is 120 degrees. And BIN right there, there's 60 degrees. All right, second page, so either flip over or bring out that second sheet. And here we go. So find the probability of throwing a dart at random and having it land in the shaded region. So here, first and foremost, I just have to think, well, it's a probability. How do I get to the shaded region? And then what do I divide it by? So I'm always thinking, since it's a probability, I'm looking for the area of the shaded region. And then I want to divide that by the total area. So again, we're assuming that this person has good aim and they're at least hitting the board somewhere. So shaded region, total area. So if I first focus on, well, what part is my shaded region? And my shaded region is really just right in here. So let me draw that medium circle right in here. Right, so I need to get to that medium circle. That much I know, but I do see this hollow cutout, which is right in here. So it's like taking out that part in the middle. So I'm looking at my medium-sized circle and I'm subtracting the small and then I'm dividing it by the big. I know that these are all circles, so I know circle area is pi r squared, and I'm also giving each of their diameters. So my radius then here must be 11, my radius here would be 7, my radius here would be 5. So again, I'm looking at pi r squared. So for the medium one, pi times 7 squared. The small, pi times 5 squared. And then the big, pi times 11 squared. So now I really get 49 pi minus 25 pi over 121 pi. It cleans up to be 24 pi over 121 pi. So since I see a pi divided by a pi, that's really a 1-to-1 ratio. So this is really 24 divided by 121. So that would be my simplified fraction. And if I type that into my calculator, so let's say that I type it in. So if I'm looking at 24 divided by 121, that gets me to the nearest hundredth, 2 spots. That 8 is going to pull that 9 to a 0. So I'm looking at about 0.2 for my probability. So if I look back at my visual, does it look like a 20% of this entire circle here is shaded? Does that feel like a good approximation? Well then good, because that's what our answer ended up being. So it's just good to have common sense and go back and see if your answer makes appropriate sense. All right, verse 6. In circle E, the measures of AEB, BEC, and CED are in the ratio of 3 to 4 to 5. Okay, so again, I don't know what their actual measures are. I just know how they're related. So I know that since these are all on this straight pathway, I know that they have to sum to 180, and I need to figure out what is the multiplier that's being applied to each of them to make them sum to 180. So I'm going to add on an x and write this as, well, first this is 3x, this is my 4x, and this is my 5x. So I'm going to build my equation, 3x plus 4x plus 5x, all equal to 180. So I want to figure out, well, what was that multiplier? So when I combine those like terms, I get 12x equal to 180, and then divide by 12, and I get that x is 15. Okay, so that tells me again that 3 times 15 would be the central angle and its intercepted arc. So right here, 45 degrees. Okay, 4 times 15, so 60 degrees for the intercepted arc and the central angle. 5 times 15 is 75. So central angle, intercepted arc, both 75 degrees. So the ratio of 3 to 4 to 5 is really the same thing as 45 to 60 to 75, right? If I took that 45, 60, and 75 and divided all of those by 15, it would get me back to a 3, 4, 5 ratio. So now we're asked for the measure of arc AB, the measure of arc BC, and the measure of arc CD, which is essentially what we just solved for. So AB right there is 45 degrees, BC right there is 60 degrees, and CD right here is 75 degrees. All right, last up, we have one of those beautiful circle puzzles that are my favorite. So here, looking at the picture, we're told that it's circle A. So A is the center of the circle. We also know that GC and BD are diameters. So that just tells us that it's gonna create semicircles for the circle, right? It's gonna make 180-degree semicircles. So first, what I usually build off of is I build off of any central angles. So if I build off this 68, I know that its intercepted arc right here will also be 68. So will its vertical angle, 68. And here, from here to here, its intercepted arc would have to be 68 as well. So to get to this smaller arc right here, I take 68, subtract the 16, and right here would have to be 52 degrees. Okay, over here, go back to that 68. Its linear pair is supplementary, so 112 here, which means 112 here as well. Okay, I also have the vertical angle, 112 in that position also, and its intercepted arc would also be 112. Okay, so I filled in all of my central angles, and I filled in all of their intercepted arcs. Okay, another thing that I see right now is that I have a tangent line right here, and I see a radius right here. So at that point of tangency, this must be a right angle. Okay, I'm going to move along my circle and look for any inscribed angles. So right here, I can see that this inscribed angle would be half of its intercepted arc. So half of 68 is going to get us 34 degrees. Okay, as I move over to this one, so here I'm looking at half of its intercepted arc right here, so also 34 degrees. And again, that makes perfect sense because what I have right here is a radius, right here also a radius. So I really have this beautiful isosceles triangle, and I know that my base angles, they have to be congruent also. Okay, let's see, next one right here, this angle right there, half of the 16, I get 8 degrees. Okay, as I move to the inside to solve more of these angles, one way to get to this angle right here would be to see that the triangle has to add to 180, and right now I've already used up 120 degrees. So what's left right here would have to be 60 degrees. Okay, another way that I could have gotten there would be to trace up, look at this intercepted arc, trace over here, look at that intercepted arc. So if I add those two measures, the 68 and the 52, I have 120 degrees, split in half, gets me to 60. So there's another way to get there because my vertex is somewhere inside of the circle. All right, then any linear pairs. So here 120, here 60, here 120. All right, last angle to get is this one right here. So here the vertex is outside the circle, so I know it's going to be 1/2 the difference between the two intercepted arcs. So I'm looking at 1/2 of here, 68, take away right here, 16. So I'm looking at what is half of 52, and I get 26 degrees. All right, so I think I filled in everything that I possibly can. So now, let's see, oh, I see a couple more things. Just right here, one more thing right there. So this angle has to be half of its intercepted arc. So if I'm looking at half of 164, I'm going to get to 82. All right, I think I've gotten everything now. All right, so a measure of arc BC. So right there, we got 68 degrees. Angle F, that measure right there was 26. Arc GB, so here's GB right here, 112. Angle GCE, so GCE, that little tiny one right there is 8 degrees. JCE right there is 82 degrees. Good thing that I filled in that last little part. CHD, so where's my C here? CHD right there is 120. BCD, that's a semicircle, so 180. All right, and then lastly, angle ICA. So ICA right there, 90 degrees total. All right, you guys, that is my review for Chapter 6. Have a wonderful rest of your day.